Are you seeing my screen? I was not able to share the PowerPoint specifically.
Yes, sir, it is visible.
It's still visible, right?
Yes, sir.
So, in the previous class, we made a conclusion about the steps by which data conversion can be done by your ADC 0848. Okay, so you can see the connection over here. You can assume that this is any type of transducer. Okay, so your channel 2 will take input signal from here. This is your ADC 0848 and this is your 8051. So whenever you need to code with one of these ADCs, you need to specifically show this type of diagram. I mean, based, not diagrams, I mean, this connection, that what is your connection. Based on this connection, your code will be done. Let me write the code, then it will be much more easier to understand. And whenever you write your code, you must write complete code. Okay, do not write without org and n. Although during the class I do so, but you should not do that during the exam. You must write your complete code.
Sir, 0AH নাকি 6AH?
0AH. I believe this code was there in your book. So I mean, writing was not that important. Still, if you're writing, that's okay. I don't have a problem with that. So let's try to explain. Okay, we are already familiar with the bit. What is this known as? Bit operator, right? I mean, this makes them equal. What is this type of term called? I just forgot. Certainly blackboard. Bit and equate are the same thing. Bit is for your single bit, and equate is for a byte sized. What are these? These things are known as what? Can anyone remind me? Directive, right? That was the word I was looking for. These are directives. Okay. So bit directive makes P 2.4 equivalent to CS. So whenever you use CS, you actually have an effect of effect on P 2.4. All right. So as I was saying, this is similar to your equate directive. So this portion is actually connected with this type of diagram. So what type of diagram you give, what type of connection you make over here, based on that you write this portion of your code. All right. So that's why I told you that whenever we write this type of codes, your diagram is important. You must show your connection, that based on what you have done this thing. So let us start. What we are doing, first of all, we are setting interrupt to 1, we are setting CS to 1, we are setting RD to 1, we are setting WR to 1. All right. Then we are writing move the value 01H to port 1. Okay, this is the port 1 over here. This port 1 you are controlling. So what you are doing, you are moving the value 0AH, not 1, sorry, 0AH. So why 0AH? If you recall from the last class, your 0AH will select channel 2 address. You can see that only channel 2 is connected. So this is also important, that which channel you have connected. So based on that, you need to provide the address over here, that the channel that you have connected to the transducer, the address of that particular channel should be sent to P1. Once again, why P1? Because you can see your P1 is connected to the data pins of your ADC. So if you connect with P3 or P4, then you need to specify accordingly. Then no operand is just for delaying some time. It gives a better what we can say, it gives a better timing. Then we clear CS, we clear WR. As I've told you that it will be better if you see the last class. So we need to clear the CS, we need to clear the WR. So what will happen if CS is cleared and WR is cleared? When CS is equal to 0, given that your RD is equal to 1, the address should be provided. Then we need to apply a low to high pulse to the WR. So you see, you have cleared CS over here. Then you need to make sure your RD is 1. Your RD is already 1. And then you need to apply a low to high pulse. Okay. So you have cleared your WR. Okay. So your WR was high. It has just gone low. Then you apply no operand, just waste some time, Then you write set bit WR, that means WR goes high. So in this portion, you are applying a low to high pulse in this particular line. So what will happen if you apply a low to high pulse? The data that you move to P1 will directly go to this ADC. Your WR will latch in the address. It will understand that this is the address from where I need to select the channel, and it will take input from the channel and your data conversion will start. All right. Then we again set CS is equal to 1.
Can you
We
repeat
set
that last part again?
All right. In the last class, we told you that when CS is equal to 0 and RD is equal to 1, we need to apply a low to high pulse to WR. When we apply a low to high pulse to WR, your WR will let the address. First of all, it will take the address, or it will read the address, and it will select that particular channel. From that particular channel, it will take the data and start the conversion. All of these things will happen when you apply a low to high pulse to WR. So you see, your WR was high, then you made WR low, and then in this particular line, you made WR high again. So in this particular line, you applied this low to high pulse. So whenever you apply this low to high pulse, you see that you already have the data in port 1 of your MUSI, which are connected to the data pins of your ADC. So whenever you apply this pulse, your ADC will read the data from the port 1, and it will understand that based on the data, I will select the channel. So this channel will automatically be selected based on this value that you have provided over here. Okay. So it will take the data from this channel, it will read the data and it will start the conversion. Is that okay? Then what you do over here is you make this port 1 as input port now. See, previously by default it was output port, or it is actually better if you make this port as output in this particular place. If you define it as output, it is actually better. However, in this place we need to make this port as input port. So look at the arrows. This is bidirectional. Okay, so port 1 will act both as input and as output. So now you are configuring the port as input port, because after the data conversion you need to read the data from ADC and you will read through port 1. All right, so we configure the port 1 as input port. Then rest of the thing is actually straightforward. We monitor the interrupt pin to go low by this particular line. Whenever it goes low, we make CS is equal to 0, we make RD is equal to 0, we provide some time, and we set bit RD is equal to 1. We know that at this stage your data will be ready to be displayed, or your data will be ready to be transferred from ADC to your microcontroller. All these things are also there in your last class. Please see the last class, the summary, then you will understand everything. Then we move the data from port 1 to to the accumulator. After that, what you do with the data is a completely different thing. In this particular code, we are just trying to show that you have selected channel 2. From that channel 2, you will read in the data will be converted and the data will be transferred to your MUSE. What you do with the data is a completely different thing. So you get the data, but there are two things that you must do. Okay, you set CS is equal to 1 so that it gets ready for the next cycle. These few things are there. You see, you call the conversion, you call the convert function, and you call the data display function, because the data that you get from here, which is stored in the accumulator, you need to convert that to ASCII. So you call a function convert, which is supposedly designed to convert your data to the ASCII. Then you call display. This is the data. This is the function that you call to display the data in your connected LCD. Now, as you can see that these two are not given because this conversion was already discussed in chapter 6 and this data display was already discussed in chapter 12. So that's why these two codes are not shown over here. However, during your exam, you must show this. I mean, your code must be complete. So you need to show this type of thing as well. So pay attention to what I'm saying right now, what I'm going to say. Say in question, say 1B, okay, say in question 1B, you need to write a code that will display some data in the LCD. Assume, just assume, okay, in question 1B, you need to write a code that will display your result on the LCD. Okay, so you complete 1B, you move on, you finally come to say set 3. Say in set 3A, you get this type of code that you need to design this thing and all. So you need to call the data display. In such case, you don't have to write this code once again. You can call the what is this code? Why I'm forgetting all these things? You can call the label, okay? You can call the exact label that you gave in question 1B to this data conversion. And within comment section, you can write that this code is available in question 1B. What I mean to say is that if you need separate chunks of code or separate blocks of code which you have already written in some other question, you can just provide the reference and specify that this code, this block of code which I need over here is already there in a different question. So please see from there. But you need to properly call the label. Is it understood what I just said?
Sir?
Yes.
Sir, I have a confusion about the channel addresses because
okay, what confusion?
Here we are using 0AH and channel 2 is selected. And according to table 13.6.
13.6, right?
Yes. Yeah, we have channel 3, which is correspond to 0AH. I'm a bit confused.
Okay, let me just check if that is the case. So, okay, these are in binary. If I go to channel 2, it is 01001. If I convert that to hex, I get 09, right? Yes. If I go to channel 3, then The data is channel 01010. The convert data है. It is channel. Yeah, it should be channel 3. Thank you for that. It should be channel 3. Okay, so if you want to give channel 2, the address should be 09H. Thank you for that. Okay, this is 09H is the address for the channel 2. Sorry for that. I mean, this is a mistake in the book. I did not bother to verify or cross check. I should have cross checked. Sorry for that. So the address of channel 2 is 1001. Yes, and that is 09H. Okay, thank you for that. All right, so what I was saying, is this portion understood, that you can call separate chunks of code from separate questions? Have you understood this portion? Come on, be quick, please. Either yes or
Yes,
no.
sir. Yes, sir.
Yeah, let me just move
Yes,
on.
sir.
Okay? We
Sir,
need to cover a lot of things. Yes.
Sir, can you explain the set bit CS in the third column, third line?
This one?
I cannot see. No, sir. Top. Yes, sir.
This one?
Yes, sir.
All right. So we write set bit. Oh, okay. This is once again analogous to the last class. You try to see the diagram. We clear the CS after for a particular duration of time. After that, again, we make CS is equal to high. Look at the figure that we constructed in the last class. We also explained why CS needs to go high. Is it okay?
Okay, sir.
All right.
Sir, what is the purpose of the no operation parts
It
in the
just,
code?
instead of calling a delay, it just gives a fraction of a time, nothing else. No operand means do nothing, but it will consume 1 or 2 machine cycles. So you are just
Sir,
giving some time.
Does it have to follow this exact pattern?
No.
as in
It
no
doesn't have to
oper-
follow.
two-time
Even-
no operation after.
Even you may completely remove this no operands, doesn't matter. The only thing is that when you are doing like this, when you are clearing the WR and then again setting the WR, in between you must insert 1 or 2 no operands, because you understand, right? You are clearing it, then you are setting it high, so it goes directly like this, so you don't have any specific time. So you can either call a small delay, or you can just provide 1 or 2 no operands. That will also do.
Okay, sir.
Okay. Let me stop sharing. Actually, I needed to draw the figure, so I used the PowerPoint. For the whiteboard. All right, now, so we discuss another converter, ADC max 1112 ADC, analog to digital converter. Now this is also 8-bit, but the only difference now is that it is a serial ADC. So far we have seen two ADCs, both of them were parallel ADCs, and we also saw how to code with them. So showing the code for one is actually similar for all the ADCs. It doesn't make any difference. Okay. So we already saw how to code, but now we need to know how to work with a serial ADC, because this is not a parallel ADC. Similar to the previous ADC, it also has 8 channels. That means you can have 8 analog inputs. And as obvious, since this is serial ADC, it has only a single D output pin. All right. So we, if you see the diagram, what is the name? So let me give you the name of the diagram. The diagram is, yeah, it is figure 13.1.2. So you can see that. All right. So if you see that figure, that is the diagram for your Max 1112 chip. So over there we have got 8 channels. The channels are also similar. We need to get the address of those channels. In a single-ended mode, each channel is used for analog input, and COM, this is another pin. This is used as ground reference, and we select input channel by sending in the control byte. This is something that we will discuss in details. Okay, control byte via the D input pin. All right. So see, these are the 8 channels. We can select any one channel for input at a particular moment, but as previous one, we need to specify which channel we are going to use. So since this is not a parallel ADC, these are serial ADC. So to read the data, you need to read the data serially as well, and you need to provide the output serially as well, because this is a serial ADC. So as I said, that we will discuss about the control byte in details, because this control byte will specify which channel you are going to select. Okay, so just keep on going, you will see all these things. All right, so there is nothing to explain about the COM or CS. let us discuss about the serial clock. So this is your serial clock input, all right? And this serial clock is used to bring data out and also send in the control byte, but it must be 1 bit at a time. So that means this is actually nothing but your clock pulses, all right? So this, I mean, based on these pulses, it will determine that how you will bring in the data or how you will send out the data. Say for example, this is the D output, that means this is used for data output. So how can we send the data output? So the digital data is clocked out 1 bit at a time at the falling edge of serial clock. So do you know what is the meaning of falling edge? Maybe you know. What is the meaning of a falling edge? Anyone? What is the meaning of a falling edge?
High to low.
1 to
Exactly. High to low, 1 to 0, whatever you say, exactly the same thing. So this portion is known as your falling edge. And this one is known as your rising edge. So this is the convention. When we send out the data, each data is sent out at the falling edge of your serial clock. So whenever there is a falling edge, your one data will be sent out. Again, in the next falling edge, your another data will be sent out. And that is just the opposite for your data input. Whenever there is a rising edge, one of the data will be taken as input, or one of the bits of the data will be taken as input. When we go for the next rising edge, another bit of the data will be taken as input. Again, we will see all these things in an example also, don't worry. But for the time being, you must understand up to this, that in every falling edge, your one bit of data will be sent out, and in every rising edge, your one bit of the data will be sent in. Not that both of these will take simultaneously, not like that. When you are sending out the data, on every falling edge, your one bit of data will be sent out. When you are reading in the data or you are having data input, then on every corresponding rising edge, your each bit of the data will be taken as input. All right, let's move on. So we already know what is VDD, so nothing to discuss over there. Now there is a new pin which is known as shutdown. Okay, this is an input pin and normally this is not connected. However, if this pin is low, your ADC will be shut down, and this is the hardware way of shutting down your ADC. And also you can use the control byte, which can also shut down your ADC, and this is the software way. All right, just this is a pin by which you can control when to shut down your ADC if you want to shut it down by in the hardware way. And reference in, this is a reference voltage, and also it dictates the step size. We have seen this type of thing in the previous ADCs as well. So up to this was your pin description of your ADC, of your MAX 112 ADC. Now we go to the control byte, the thing that we had been saying so far that we will discuss. Okay, so now we are going to the control byte. Well, the control byte is fed into the MAX 1112 serially as expected, and 1 bit at a time via the D input pin, and we know that it will take place on the rising edge or falling edge of serial clock. Which one? When you are feeding in the control byte, it will go in the rising edge. Good. And then one convention is that the control byte must be sent in with the MSB going first, and it must be set to high. That means your control byte, in your control byte, your MSB will always be 1. Whenever your MSB is 1, your ADC realizes that this is a control byte. So it works accordingly. Okay, so this is a must. Let us see how it will work.
Sir, the control byte, it is comes, shut down, or pauses.
বুঝি নাই
Sir, the line, sir, the control byte, it comes, shut
No,
down.
causes
Causes shut down.
Sorry.
Sir, could you give some to write sometime?
Okay.
Okay, sir. Thank you, sir.
Again, this is there in your book. So if you don't want to write, that is fine. Just try to understand whatever I'm doing. All right, so I think this is quite straightforward. Your this pin MSB should always be 1. There is no confusion about that. Then we have got these 3 pins, which are actually responsible for selecting which channel you want to use. We have got 8 channels, and the corresponding address of all these 8 channels are given. Then we have got some other pins which are specified as unipolar or bipolar. So when this pin is 1, you specify that it is unipolar. That means the digital data output will be given in binary from your ADC. Okay, so from ADC, the output that you will give will be in binary. So that's why this is known as unipolar. And when we say bipolar, that means the output that you will give, or the output that the ADC will give, will be in 2's complement. Okay, so it is again user dependent. The user will define how he wants to display his answer, either in unipolar or in bipolar. Then we have got single-ended mode or differential mode. When we have this pin as 1, we mean that this is a single-ended mode. We already know what is single-ended mode. In single-ended mode, out of the 8 channels, you can use only 1 channel at a single time. Okay, this is known as a single-ended mode. There is actually another mode which is known as differential mode. We did not discuss differential mode. In differential mode, actually, you can use 2 channels simultaneously, but they act as differential circuits. Okay, so you don't have to worry about this. By default, you can consider that it will always be single-ended mode, since we did not discuss about the differential mode. Then we have PD1. So if the value of PD1 is 1, that means it is working, your ADC is working. And if it is 0, it means powered down. Remember, this is not shut down. Okay, this is powered down. This is equivalent to, say, sleeping mode of your PC. Okay, you just take the lid down, it goes to sleeping mode. So that is something similar to this powered down. So if you do not need to use the ADC for some specific period of time, you can simply put 0 in this particular pin. So it will go in the power down mode and it will save some energy. And finally, we have PD0, which controls which clock you want to use. If you want to use external clock, then you provide 1 in this particular pin. And if you want to use internal clock, you provide 0 in this particular pin. So is it understood, everyone? If you have understood,
erases the data already in the ADC.
Say again, what?
Does the sleep mode erases the data?
No. It does not erase. It does not erase anything. I mean,
shutdown does, right?
Yes, shutdown will erase everything in your RAM memory location, right? So that is also a similar thing over here. Okay, so if you have understood up to this, let's try to do something. Say we need to select channel 0, then we need to have a single-ended mode. Okay, then we need to have unipolar operation. Then we need to use the internal clock, and of course it will be operational. So if these are the conditions, what will be your control byte? Your CPU will be what? Say bitwise. Anyone? I mean, it should be very easy from here. What should be the first bit for this particular problem? What should be the first bit?
One.
Okay, then
0, 0, 0.
0, 0, 0. Then
1,
maybe, right? 1, 1. Good. Then
1,
then
0.
exactly, good. So if you convert it into hex, you end up getting 8EH. So the same problem, say instead of channel 0, we want to select channel 1. So what will be the only change? What will be the only change if you want to select channel 1? In this portion, the change will take place, right? Instead of 0, 0, 0, we will have how much for channel 1? We will have
0, 0, 1.
0, 0, 1, right? So 1, 0, 0, 1, then 1, 1, 1, 0. If you convert it into hex, most probably you will get 9E, because this is just the following number. So you are supposed to get 9E. This is for channel 1. So you see, this is how your control byte works. You specify your control byte. We will see in a code within a very short time. So this is how your control byte works. Okay, you send in a code. and then you need to, the most important thing is you just found out how, I mean, what is the control byte, but now the thing is how will you feed the control byte to your ADC? So let's see that. Give me some time. Again, I need to use the PowerPoint because I have to use some figures and all. Just a second. That's why physical classes are better. I could have used PowerPoint and I could have used the board simultaneously. That should have been much better. Okay, for the time being, I'm leaving the screen display on till I prepare my PowerPoint. All right, so I believe it is visible, right?
Yes, sir.
Let me write the code. After that, I will explain. All these figures are there in your book, okay? So you don't have to bother writing. Just try to understand whatever I'm saying. I'm writing this double comma does not mean in the exam you can do that, okay? I'm doing it just for saving some time. So don't do that in the exam. But this is just the code for sending in a control byte. So if you understand this thing, then sending out a control byte or doing an entire code will be very similar. Okay, nothing to worry about that. All you need to do is understand how you can send in a control byte. The other things will be very same. Huh? So again, the first portion is equivalent to your connection, how you have given your connection. As you can see, the CS is connected to 2.0, serial clock is connected to 2.1, then BIN is connected to 2.2, and so on. So one thing to mention over here is that definitely you will get one of these questions from ADC. I don't know how many questions you'll get from ADC, but you will get one or two. Whatever you get, you definitely have to give your connection diagram based on you. I mean, you need to specify which pin goes where. So time and again, I'm saying, please don't copy from your friends or don't give the exact same connection which is there in the book. Try to give your own connection. I mean, changing these pins, I mean, is not a big deal at all. Just instead of using, say, port 2, use port 3 or port 4, or use some other pins. Okay, this is not a big deal. All you have to do is you need to change this portion of your code according to your design. So if you can just do this much, and you can use some separate pins, you know, at the very beginning, I will have the impression that you have done it by yourself. So have that impression. Other than writing this exact same pin and all these things, don't keep me in confusion that whether you're copying from the book or taking help from some friends. Don't take me in that confusion, because it creates a negative impact on your script when I check that. Rather than that, if you have a unique set over here based on your connection, at the very beginning, I will have a good impression that no, he is trying at least based on his own connection. Okay, so please do those things. All right, so this is how we specify based on the connection. Now we move the value 9E, as we have seen previously that this will select channel 1. We have already seen this one. It will select channel 1 and it will be unipolar and all these things. It will use the internal clock pulse. The output will be in binary mode, all these things based on this value. Then we move 8 over here, because we know that control byte contains 8 bits. So this one is actually your loop control variable, as you can see from here. So that's why the value is 8. Then we clear CS. We know that CS needs to be cleared to activate this chip. So we are clearing the CS and we are clearing the carry. Why we are clearing the carry? Because this is a serial input or serial output, right? So if you want to send in data serially or output serially, you obviously need to use this carry flag. So this is a very important step. You need to make sure that your carry is cleared at the very beginning. Then what we do, rotate left carry the accumulator. You see the accumulator already contains your control byte. So you simply move one to the carry. So the leftmost bit will move on to the carry. Then you move the carry to this D in. However, when you write this line is not executed right away. I repeat, whenever you write move D in comma C, the value of carry flag does not move in this D input right away. It waits. It waits for what? Rising edge or falling edge of serial clock?
Rising.
Exactly. It waits for the rising edge of serial clock. Okay. So you have already given the command, but it does not move. Then you see you clear the clock pulse, then you call a specific delay and you set the clock pulse. So this is where you provide your first rising edge and the first value of carry will move on to this D input. Again, you call the delay and you repeat this process, so on. So this is how you send in our data serially, and it takes place on every rising edge, as you can see over here. See, this is the pin values which are showing. So every value, it will go on every rising edge of your serial clock. So if there is any question, please ask now. See, once you get the question, the code will be pretty big when you write in your exam, because this portion is your first portion of your code that you have to write. You need to specify the control byte. You need to send in the control byte. After that, you need to execute the conversion like the previous code. So you need to convert. After converting the data that you have, you need to send the data serially as output. All right. So you need to configure that, and don't forget to configure this pin as input after you have sent in the data, because afterwards this one will act as input or not. No, sorry. This will not work as input. Sorry. 2.2. Yeah, we already have data for input. Sorry. Yeah. So 2.2 will work as input and 2.3 will work as output. So we don't have to worry about that thing. We have already specified all these things. So this code will be a pretty big one. And whenever again you write a call delay, so if you already created a specific delay in some other question, you can simply call that delay from that particular question. You don't have to design the delay over here once again. But in the comment section, you must mention that the delay subroutine has already been generated in question something 2A or some other question. So you will call from there. So you can do that. All right. So if there is any question, please ask now. If there is any question, please ask now. One thing I forgot to discuss, I will discuss it now. The significance of this one. Why is it 2.56 volts? Sorry, I forgot to discuss that. So let's finish by, I should have discussed this before I have gone to the code. Okay, anyway, so let me discuss it now. So yeah, what I was supposed to discuss is reference in voltage and step size. Okay, so please try to understand this portion. Okay, so assume that your VDD is connected to plus 5 volt and your reference in, that is REFIN, say this is connected to analog ground. Okay, say this is connected to analog ground with 1 microfarad capacitor. If this is the case, that is your VDD is connected to plus 5 volt and your reference input voltage is connected to the analog ground with a 1 microfarad capacitor, then the voltage input or the reference voltage that you get is 4.096 volt. All right. So if your reference voltage is 4.096 volt, then can you calculate the step size? What will be the step size for this particular case? Is there anyone who can remember? How do we find it? If the reference voltage is 4.096, then what is the step size? Tell me.
Divided by 256.
Good. 4.096 divided by 256, which will give you 16 millivolt as the step size. And I will not be discussing this again, why and how we got 256. But say now, instead of connecting this reference in voltage to your analog ground, you have connected your reference in voltage, say to 2.56 volt, which was the case in our previous connection. Okay, if you remember or if you have seen from the book, you will see that the reference in voltage was connected to 2.56 volt. In that particular case, your reference in voltage is indeed 2.56 volt. So what will be your step size? Then your step size will be 2.56 divided by 256, which will give you 10 millivolt. So in our last example, the step size that we had was 10 millivolt. So again, you need to specify what is your reference voltage. So based on your reference voltage, you will have your step size. So this is almost, I mean, this is like a design problem. I mean, if you get any question from this chapter, that is chapter 13, it will be a design problem because everything depends upon you, which channel you select, how you give the connection, what is your step size, which ADC you use, that might also be given. I mean, it might be open. I don't know how I'll make the question, but a design problem should be as open as possible. Okay, so I'll make it as open as possible. The difficult thing is that you need to know the pins of this thing. I mean, understanding the description connection is all easy, but you need to remember the pin configuration, which ADC contains how many pins and all these things. So that is the difficult task. But other than that, if you just understand this once, it is very easy. There is nothing different or difficult. The only difference is in Max 112 is that since it is serial input output, so you need to design it based on the serial clock. So pay attention to your question which is given. Okay, it might happen that I have told you that say you are using the external clock pulses and you are said to design a clock pulse of particular frequency. So that becomes a very big design problem because you need to specify, you need to design that thing, all these things, then you need to give the connection and all. So it becomes a bit complicated. So be careful, okay? Whatever you do in the exam, at least if you see that the time is very short or something like that, at least make me understand that you understood the question, and you explain first two or three things, and you can just say that if you don't have time, you can just say that in this way we can find rest of the things, okay? At least make me understand that you got the gist. All right, so to finish chapter 13, we are almost at the end. There are a few things as usual for your self-study. So reading out digital data. This is related to the last ADC that we discussed. Then section 13.3. This is your self-study. Not big, okay, very small. And you can exclude section 13.2. All right, so that's it. With this, we finish chapter 13. And now we'll move on to chapter 14. Okay, is there any question in chapter 13? You can ask now. Yeah, so if you do not have any question, let us move on to chapter 14. We will not cover everything of chapter 14. Okay, so please try to pay attention to the things that we are covering over here. I can still see a lot of participants. Are you really there with me? Or you are just staying over here? কিছু বুঝতেছ না, আজকে কিছুই বুঝতেছ না বলো তো?
স্যার ট্রাই করতেছি স্যার।
একটু আসতে গেলে ভালো হয়।
একটু আসতে গেলে ভালো হয়, সময় তো নাই তোমাদের, তো আর একটা উইক মাত্র। এই উইকেও তো এখন ডাবল ক্লাস, তো ব্যাক টু ব্যাক ক্লাস। এই ক্লাসটাই দুইটা ক্লাসে নিলে এত প্রেশার হইতো না। But আমার actually এটা personal problem এর জন্য I did this, so I apologize for that. I'm taking 2 back-to-back classes.
স্যার সিলেবাসটা তাহলে একটু কমায় দেন।
সিলেবাস কমাই দিলে তোমাদের কোনো লাভ আছে আমাকে বলো তো? তোমাদেরই তো লস, তোমরাই তো শিখবা না। সিলেবাস আর বেশি নাই, এই চ্যাপ্টার 14 এর ছোট্ট কিছু জিনিস, আর নেক্সট উইকে জাস্ট একটা ক্লাস নিব, ঠিক আছে? দুইটা ক্লাস নিব না। চ্যাপ্টার 15 এর জাস্ট হালকা কিছু জিনিস দেখাই দিব, দ্যাটস ইট। চ্যাপ্টার 17 এ ছিল, সো চ্যাপ্টার 17 বাদ দিব। চ্যাপ্টার 17 was that connects your motor with your microcontroller, okay? So that becomes, ওটার জন্য অ্যাকচুয়ালি এক উইক টাইম দেওয়া উচিত, আদারওয়াইজ জাস্ট সেলফ স্টাডি দিয়ে ছেড়ে দিলে জিনিসটা খারাপ দেখায়। the things in motor I should discuss. So যেহেতু সময় নাই, আমি চ্যাপ্টার 17টা বাদ দিব, বাট 14 15 পর্যন্ত শেষ করতে হবে। Alright, so let us start. Memory address decoding. Okay, so let me discuss this, why we need this portion first of all, okay, at the outset. Sometimes what happens is that we connect external memory blocks, okay, to the MUSI 8051. So we need to specify that if you are connecting an external memory block, then how can you specify the address? How do you get the address? How can you get the data and all these things? So this one is completely, this chapter will completely deal of how you can connect an external memory block with an ADC and how those things work. So let's start. This chapter is a bit descriptive again, so it will be easier for you to understand. Code is there, but very small portion of code. Okay, so let me explain up to this. These are again actually quite straightforward. If you just read, you will understand. So the CPU will provide the address, and we need to have a decoding circuitry which will select the memory block that we want to use. Normally, our memory chips have one or more pins called the CS or chip select. Sometimes it is also known as CE or chip enable. Okay, which must be activated for the memory's content to be activated. Very obvious. And the data pins of the CPU is connected directly to the data pins of the memory chip. We'll see all these things in a while. We'll see one example. So you will see all these things. Again, these things are there in your book. So I'm just summarizing these things. Again, this is quite descriptive, but we will see the connections, don't worry. So normally we have the control signals which are read and WR, that is read and write from the CPU, which are directly connected to the output enable and write enable pin of the memory chip. When we will go for the pins or when we will go for these chips, you will see all these things. And in case of address bus, I think this one will be clear if you go with an example. I'll show this example just right now. If you go, I mean, in case of address buses, the lower bits of the address from the CPU will go directly to the memory chip address pins. But the upper ones are used to activate the CS pin along with some other pins as well, as we will see. So the upper ones control the other pins of the memory chip, and the lower ones will directly go to the address pins. And see, it is the CS pin that along with RD or WR allows the flow of data in or out from the memory chip. I mean, until and unless you do not enable the CS pin, the memory chip will not be activated as usual. So you need to activate those things so that your memory chip will work. So the thing that we should see or focus over here is we need a decoding circuitry. Okay. Now we can make this decoding circuitry using simple logic gates, I mean, which you can do or see by your own. That will not, I mean, that is one of the way which I will not discuss. Rather, I will discuss a dedicated decoder which is there for this particular purpose. Okay. So let us discuss a dedicated decoder, then hopefully you will understand all these things. And you would have understood this explanation very well if you just, I mean, if I could just share the figure as well. So it will be better if you just write this portion, because I'll share the figure after this, so you can correlate. Yeah. Right, so I've just said a few things over here. This is a decoder, very obvious. This is a decoder. This is known as a 3 to 8 decoder. That means we'll have 3 inputs, and we can have 8 active low outputs from Y0 to Y7. You'll see what is ABC and what is Y0 to Y7. And each Y output is connected to CS of a memory chip. That means you can connect up to 8 memory chips using this decoder. So you can select which memory chip you want to access and so on. So let me share some figures so it will be easier for me to explain. It is there in your book, so I think let me share directly from the book. It will be easier for me also. All right, you can see the book, right? Can you see the book?
Yes, sir.
Yes, sir.
Okay, so see, this is the decoder that I was talking about. Okay, 74LS3, 74LS138 to 8 decoder. So as you can see, we have got 3 inputs which are ABC, and you can select up to 8 channels which are there. VCC is VCC, ground is ground, and we have got some other enable pins which, as you can see over here, G2A, G2B, and G1. So this table is actually important. Okay, so try to understand this table first of all. Say you want to select a specific channel. So how do you select a specific channel? So start from here. If you want to select Y0, then you need to make sure that G1 and G2 has these values. That is, G1 is high and G2 is low, and all of your A, B, C are low. So if this is the configuration, then you select channel Y0. As I have already said that these are, you can see over here, these are active low outputs, right? So whenever one of the channel has active low, that channel will be activated. Actually, you can see from here also, these are actually inverted. So if you provide a low input, ultimately it will become high, and that's how the channel is being activated. So let's not get into all those details. You can just follow this specific figure. So based on this specific connection, part of a connection, I should not say full connection, based on this specific connection, you can see from here. So similarly, say you want to select channel Y6. So see, for Y6, your value should be in C should have 1, B should have 1, and A should be 0, and G1 should be 1, and G2 should be low. Again, this is not very difficult to keep in mind, because you can see G1 and G2, this configuration is same. G1 is always high, G2 is always low. You can forget the first two because we do not select any channel in the first two, so forget about those two. Just focus on this portion, right? So this is equal to 0, 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, or so on. So just simply the binary format. So you need to remember this, because you need to specify which channel you are going to use or which output you are going to use from the channel. And based on this, your specific memory block will be specified by this decoder. I mean, based on the value that you provide using these particular pins. So do you have any question up to this? Okay, so if you don't have any question, let's see some examples. Okay, second. Obviously, now I need to have a figure. I need to go to PowerPoint now. So I believe you can see my screen, right? Try to focus, okay? If you just understand this class, I mean, a lot of things will be covered actually. So please try to pay attention. Okay. So look at the connection again. This connection will be given by you. So this is a memory chip, 4K into 8. This is a memory chip. This is your decoder, which is your just one that we have covered, 74LS something, whatever the name. Okay, that is the decoder anyway. So look at the connection, and your MUSI is there somewhere. I mean, all these data lines are coming from your MUSI. So you control from the MUSI, from A0, all these things are connected to your MUSI. So you control from this MUSI. So what is the thing? I have provided this table for the time being, but it will not be provided during the exam. Okay, you need to, since this is the first time, so I have provided this table so that you understand. Now, say from this particular diagram, you are saying that find the range of address. Okay, say find the range of address. On the range of address for say Y4. Okay, we have got Y4, which you can see that is just connected. So we need to find the range of address which is connected for Y4. So how we can solve it? The way you can solve it is, first of all, you have to see that how many address pins or address buses are there. I mean, all the pins that are starting with A are your address pins, and all the pins starting from D are your data pins. Okay, so for specifying the address, we are interested only in the address pins. So how many address pins do we have? we have from 15 to 0. So we have got 16 address pins. So let's write that. Let me just take A as common. Okay, so it will be 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so if these are your address pins, so your question is, you need to find the range of address for Y4. Okay, so if these are your address pins, can anyone tell me what should be the value in A15? What should be the value in A15? See, A15 is connected to what? G2A prime, right? So do you have anything over here that is G2A prime or something like that? Or yeah, G2. Yeah, I think it is there. Yeah. So see from here. So G2 will be connected to which pin? If we want to select Y4, look at the diagram. What should be the value in A15 in G2? You can simply consider it as G2.
Low.
Someone said 0. If you don't understand the question, you need to ask why, or you need to ask again that, sir, I did not understand the question.
Sir, but it is G2 prime, so it will be high.
No. You don't have to worry about that. I mean, if you see the previous diagram again, then G2 prime is again your, it is automatically inversely connected. So you don't have to worry about those things. Simply, you can consider G2 as your G2A, and you can consider G1 as your G1. You don't have to worry about G2B at any time. So whenever you see G2, you can consider it as G2A. Okay, and because G2B will always be grounded. Okay, so this one becomes 0. What should be the value in A14? So A14 is connected to C. So what should be the value in C? What should be the value in C?
High 1.
Exactly, very good. 1. See, how we are understanding this thing is very obvious. We are trying to select the range for Y4, right? So look at Y4. Your Y4 becomes active in this particular row. So just look at this row. If you look at this row, you will get all the connections. You see, G1 is high, G2 is low. I don't have to worry about G1. G1 is automatically high. So G2, I have made it low. Then C should be high. So C is connected to 14. So 14 is high. Then B should be low. B is connected to A13. So B should be low. Then once again, A should be low. A is connected to 12. So this should also be low. Now, the rest of the pins from A0 to 11, as you can see, they directly go to the address pin of the memory chip. So what can be their values? So their values can be all zeros, or their value can also be all ones. Sorry. And their value can also be all ones. Okay, even if this becomes 1, the previous connection will always be same. This portion of your value will be fixed. It will always be 0, 1, 0, 0. But this portion can have all zeros, or it can have all ones, or it can have any combination within these two range. So that's why the question says find the range of the address of Y4. So what should be your answer? Your answer should be, you convert this to hexadecimal and you will end up getting 4000H. If you convert this to hexadecimal, you will end up getting 4FFFH. Okay, so that means this is the range of the address which is applicable for Y4. Okay, so the question is find the range of address for Y4. Your answer is the range of address for Y4 is from 4000H to 4FFFH, and this is your answer. Please try to understand this portion, because this one is very simple and this one is very easy. So you really need to understand this portion. Karo kono question thakle please ask. If you have really understood, can you solve for Y2 and tell me what is the range? Just do it for your own benefit. it will save a lot of your time in your home. Just try to find the range for Y2 and tell me.
স্যার y4 এর জন্য কি আবার স্যার 0 এবং 1 গুলো কিভাবে পাইতেছি আরেকবার দেখাবেন স্যার?
বুঝিনি, Y2 এর জন্য আরেকবার দেখাবো?
স্যার y4 এর জন্য স্যার 0 এবং 1 গুলো স্যার কিভাবে পাইতেছি আরেকবার যদি বলতেন।
আচ্ছা, okay, fine. Okay. So for Y4 I'm explaining again, okay?
Thank you, sir.
So first of all, try to see this row. Your Y4 will be low in this particular row. That means this row will give you the connection for your Y4. Now look at these connections, okay? All these connections are already given. I mean, it will be based on you, how you give the connection. So you don't have to worry about G1. G1 is already high. G2 is G2B. You never have to worry. It will always be grounded. So you have control from this one, A15. So A15 is just assume this as G2. So assume as G2 and see what is the value in G2. The value in G2 is low. So that's why A15 becomes low. Then go to C. C is your A14. So what is the value of C over here? C is high. So we have given 1. Then again low for B and C. So B and C is 13 and 12. So these are low. So this first 4 pins is connected to your memory decoder, right? So these are the values that you get from this particular table for the memory decoder. But these pins are directly connected. These address pins are directly connected to the address pins of your memory block. So that means these values from here, these values, what is the minimum value that they can have? The minimum is they can have all zeros and the maximum is they can have all ones. In between, they can have any combination as well. I mean, you might write that this is 0, 0, then 1, 0, 0, then 1, 0. I mean, any combination. So the question says, what is the range? So the smallest address or the minimum address that you can have for this particular block is all zeros. And combining this, the address you get is 4008. So that this is the starting address for this memory block. For this particular memory block, this is your starting address. And what is the last address that you can access from this memory block? The last address is this one. This is the last address that you can access from this memory block. That's why the question says find the range of the address. So the range is from 4000H to 4FFF8. In this range, you can select any address from this memory block. Because see, the MSB for this hexadecimal number is fixed, because this one specifies that you are selecting this piece of memory block. Okay, if you had another memory block connected to Y6, say we have got another memory block connected to Y6, then for Y6 your connection should have been like this. I mean, the first 4, I mean, this MSB should have been based on this connection, but the lower range, that is from 00H to FFF8, it will always be same for all the memory blocks. Only the first bit in your range will change in your hexadecimal number, but rest of the things will be as it is. So have you understood now?
Sir, why have you selected that particular row for Y4?
Okay. Why you have selected that particular row?
Yes, sir.
See, in the description, I have told you that these outputs are all active low. That means whenever these outputs become low, they become activated or they become able to activate another memory block. So see, this memory block over here, this is connected to Y4. So come to this table and see when your Y4 becomes low. So look at Y4. You see Y4 is high. Over here, this becomes low. So when will your Y4 become low? Your Y4 will become low for this particular combination of these pins. So that's why we have selected that Y4 in order for Y4 to be low. This is the configuration that we need in this particular pins. So that's why we have selected in this way. Have you understood now?
Oh, okay, sir. Thank you, sir.
All right. So just tell me, you don't have to do. Can you at least find the range for Y2? Can you do that?
Yes, sir.
Or Y0 or Y7 for any case. I mean, you can do
Yes,
this.
sir.
I mean, you should be able to do this. And don't worry, I will not, I mean, make anything complicated with this type of connection. I mean, over here, this is inverted, so it will always be inverted, okay? I will not, I mean, if I give the connection, I will not make any issue over here. But if you are drawing the connection, and you forget to make this invert, then you need to take that into your own account. Your everything will change over here if you don't give this invert, I mean inverting terminal. So it is up to you. So if you are giving the connection on your own, make sure you provide connections like this so that it does not become more complicated. All right, so let's move on. As I told you, we are in for a long class, okay? So have patience. Okay, so if you have seen your pin diagram for your 8051, I know that we have never paid any attention to that, but now at this particular stage you need to know the pin configuration of your 8051 because you are connecting to external pins and external memory blocks and whatnot. So you need to know which pin works as what. So it will be better if you know the pin diagram or pin configuration of 8051. And by the way, the course itself is 8051, right? So it is very obvious that you at least know the pin configuration of your 8051. So if you see the pin configuration, you will see that we have got 4 ports, right? Port 1, port 2, port 3, and port 4. You will see that in port 1 is simply port 1. Nothing is there in port 1. But when we go for port 0, beside port 0, there are a few things written like AD0, AD1, and those things. Beside port 2, there are a few things written as A15, 14, and all these things. That means your port 2 will always be your address pins in this particular example. See. So your port 2 will always be your address pins. All right. Then in port 3, we have got few things like T0, T1, WR, RD, RXD, TXD, and all these things. So, I mean, just pay attention. I mean, you need to know what are those things and that those things are there already. So now we'll see description of some of those pins which we will need. Okay. So let's start. Okay, so there is an EA pin in your 8051, and that is your pin number 31. So if you have that figure, I mean, it is there in your book, it is there in chapter 4, it is there in chapter 14, everywhere it is there. So you can see the configuration, pin configuration of your 8051, and you will see that there is an EA pin, which is your pin number 31. So let us see, we discussed about this EA pin very briefly in one of the labs. So let us discuss it now. Okay. So let me say a few things over here. So your EA pin, right? So your microcontroller 8051 has an on-chip ROM. We all know that it has an on-chip ROM. But very often what happens is that what we do with the microcontroller is we constantly burn codes in the ROM space. Okay, we make new codes, we burn, then again we run, we simulate on all these things. Due to this reason, very often within a very short period of time, your ROM gets, I mean, it just stops working. Okay, it just stops working. So what we need to do is that in that particular time, in that particular case, when our on-chip ROM is not working anymore, then we need to use some external ROM. Remember, we are talking about ROM, okay, ROM. We are not talking about RAM. We are talking about ROM, ROM. All right, so it becomes, I mean, it just stops working. So we need to use some external ROM. Even at sometimes it happens that the internal ROM that we have is not sufficient. So again, we need to use this external ROM. So the concept of this external ROM is so popular that there is a microcontroller MUSI, which is your 8031. The one we are using is 8051. There is another microcontroller which is 8031. The only difference between 8031 and 8051 is that your 8031 does not contain any on-chip ROM. Okay, it does not have any on-chip ROM. That is the only difference between your 8031 and 8051. Your 8051 has an on-chip ROM and your 8031 does not have any on-chip ROM. So whenever we use 8031, every time we use, we need to use the external ROM. Similarly, if your ROM gets wasted in your 8051, also then your 8051 becomes like an 8031 actually. So you need to use that using an external ROM. So how we can use the external ROM? We need to make sure that our EA pin, this pin is connected to ground. So whenever this pin is connected to ground, automatically your MUSE will understand that there is a connected ROM which is external. So it will fetch the program code from the external ROM. All right. Now let's move on.
Sir,
Hmm.
the first line, is it 6K bytes or what?
64 kilobytes. Okay, let me write that again. Sorry. All right, so as I was saying that now we can connect external ROM to our 8051 or 8031. I have already told you the difference between 8031 and 8051. So we can connect the external ROM, and if you remember, your program counter is responsible for having the data from your ROM area. Okay, so your program counter, as we already know, it is 16-bit. That means it can access up to 64 kilobytes of program code. So the largest external ROM that you can connect can have memory space up to 64 kilobytes, because that is up to which your program counter can access. Now, definitely you need to provide the address, right? So the address is provided using both P0 and P2 because each is 8-bit. So we need a 16-bit address, right? So to provide that 16-bit address, we use both P0 and P2. Now, I've told you just before that in your P0, in the bracket, I mean, all your ports in P0, is written as something like this, AD0. Similarly, for P0.1, it is written as AD1 and so on. The meaning of this AD is it can be address or it can be data. So your P0, as you can see over here, it provides address, but see over here, P0 can also provide the data bus. So that's why it says that P0 can provide both address and data. So we need to know when P0 provides what. If I go to P2, it is written simply like this. Say P2.7, it is written as A15 and so on. That means it is only the address pin. Okay, and also at the same time, look at the numbering. This is 0, 1, and this is 15. So that means your P0 provides the lower 8-bit of the address, and your P2 provides the upper 8-bit of the address. And your P2 can only provide the address. It cannot provide the data. That's why in the bracket it is written as A15 or A14 and so on. But now the question is, P0 provides both address and data. So how do we understand when it provides what? There is another pin in your MUSI, which is ALE. This is your pin number 30. Okay, in your MUSI. So this pin number 30 controls this P0. When the value in this particular pin, that is ALE, is 0, then your MUSI understands that P0 will provide the or will be used for the data path. And if the value of ALE is 1, then P0 will be used for the address path. And we already know how to configure P0 as input and output. So that is a different thing. Don't get confused with input, output, and these things over here. This is just specifying how your MUSI will use the port 0. Will the port 0 be used as a data path or will it be used as address path? So this is what you specify. If I get back to the previous one where we connected the decoder, the complete connection with your MUSI was not given. Okay, so if you complete the connection, you need to remember that your address pins, that is from A15 up to your A8, will be given from port 2, and the rest of the connection will be given from your port 0. So please don't get confused with all these things. Okay, you need to be very clear about these things. Okay, so if you have any question up to this, I don't know whether you are being able to follow or not. If you have any question, please ask if you are being able to follow for the time being. All right, no questions, so let's move forward. Then there is another pin which is PSEN. Okay, so the last pin that we have is PSEN. This is very, this one is actually easier than the rest. This is also very straightforward. So this is an output signal for your microcontroller, and it must be connected to the output enable. As you can see from here, it must be connected to the output enable of external ROM. It should be external ROM of the external ROM containing the program code. Okay, so this is how we complete the connection diagram. Your PSEN is connected to the OE pin. So if your output enable is high or low, based on that you give the value in PSEN to activate that specific memory block containing the ROM area or the specific ROM. Okay, so that was all about your section 14.3. Okay, now let us move on to 14.4, and this is the last section. These are the 3 sections that we need to cover: 14.2, 14.3, and 14.4. We are almost at the end, okay? Just have a little more patience. All right. So we discussed a few things about this when we are talking about when we are in chapter 5. When we discussed instructions like move C or move X, then indirect addressing mode, all those things when we were discussing, then we discussed this thing briefly. So let's discuss it again. So your 8051 has 128 kilobytes of address space. Remember, this is external, okay? I mean, this is there within your 8051, but this is treated as external memory. So it has 805, your 8051 has 128 kilobytes of address space, of which the first 64 kilobytes is set aside for the program code, and the other 64 kilobytes is set aside for the data code. Now the program space is accessed by the program counter. All right, the program counter can access those things. And if you are trying to access the data memory, which is the rest 64 kilobytes, then it can be accessed using the DPTR pointer, and the instruction that should be used is move X. If you recall from chapter 5, your move C was used for the data portion, and now we use move X. Sorry, your move C was used for the code portion, where C was specifically for code, and now we use move X for the data portion. Okay, so these are the two differences between your data memory space of this 128 kilobytes. Last thing.
Sir, can you go to the previous page? Thank you, sir. Done.
The last one is just a second. My laptop is running out of charge, so let me just connect the charger. Just a second. Okay, so this is the last one. So now say you have got two ROMs, okay? So we are talking about ROM from the very beginning, and we saw that the ROM can be used for both program code and for data as well. Okay, so to fetch the data, we need to use the instruction move X, and to fetch the code, we need to use the instruction move C, as we have seen. Now, for ROM containing the program code, your psen is used to fetch the code. Remember, your psen is responsible only for fetching the code. But however, if you have a ROM which contains the data, then your RD pin is used to fetch the data. So finally, let's just see a connection diagram that will hopefully explain all of these things that we are learning for so long, or we are seeing for so long. Let me show it from the book directly. It will be easier. Yeah, let me stop sharing. Okay, this is from your book. Okay, so this is the diagram, I mean complete diagram, which explains all of these things that we have been doing so far. So try to see. Obviously you can see my cursor, isn't it? Can you see my cursor, the hand?
Yes, sir.
All right, so you see your pin 3.7. If you see the diagram pin configuration of your MUSE, you see that pin 3.7 is known as your RD pin. So what we just said, now say we have got two ROM. One contains the program space, or the program, or from where the program will be fetched, and from here the data will be fetched. So if data is fetched, then see we need to connect the RD pin, because that is what we just discussed. The RD pin will be connected to the output enable pin. And if we need to access the program code, your psen is connected to both chip enable and output enable pin. All right. Over here, they are using some circuitry to activate this chip enable, which is done. I mean, you don't need to bother about this because we did not discuss, but of course you can go through it. This one is your address decoder. As you can see, the addresses are coming from your port 0 and port 2. Look at the complete address. Starting from AD0 up to this, all the addresses are coming from port 0 to port 7. And finally, we have got ALE pin. You can see that ALE pin is grounded. It is written over here G. So if ALE pin is grounded, that means we will be using external ROM. So which ROM we'll be using will be dependent on this pin 3.7 and your psen pin, PSEN pin. Okay, and these are the your address and data pins. Nothing. I mean, port 0 can be used for both address and data. So that's why the pins that goes to this memory decoder are your address pins, and you can see the similar pins are connected to the data pins of both the ROMs. So these are your data pins. So when will your address or data pin be selected will be dependent on your ALE. For the timing, it is grounded, but it can have both the states. It can be 0 or it can be 1. So based on that, you will select whether your port 0 will be used as address or will it be used as your data pin. And for port 2, you can see they are dedicated only for the address pin. So this is your diagram that explains more or less everything that we have been doing or trying to cover so far. Okay, so if there is any question, I know you will not have any question because I don't think you have understood the complete picture, but you will. So
Sir, what is port 0 doing over here?
Port 0 will provide your both address and data. This is just the connection diagram. This is just showing you that port 0 will provide address if it is connected to this memory block diagram, and it can also provide the data. As you can see, the data pins of the external ROM are directly connected to your port 0. So port 0 can provide both address and data based on this ALE, and your ALE can be either ground or 1. Okay, so based on that, your port 0 will be decided. Is it okay?
Yes, sir.
Okay, so just to bring in the summary, okay, let me stop sharing. Let me get back to that. Just to make the summary, in chapter 14, okay, in chapter 14, just go through. I have already covered the most of the things. Just go through article 4.2, 4.3, and 4.4. Sorry, 14.2, 14.3, and 14.4. Only these 3 articles are needed from chapter 4. Okay, and I have covered most of the things. Of course, there are some examples which are very easy. Just see the examples. The connection diagram is the main thing that you need to understand, because the coding portion, if you have completed up to chapter 11, you know how to code. So I don't have to worry about that. So just go through article 14.2, 14.3, and 14.4. Inshallah, you will understand everything. And also we have covered chapter 13. I have already told you what are the things which are included in chapter 13. All right, so that's all I wanted to cover. In the next class, I will cover chapter 15. That is also not all. I will specify which things we need to cover, and I will cover all of the things from chapter 15. And that will be the end of your syllabus for this course. Okay, so that's the end of the class. If anyone wants to say anything, you can stay back. The others are free to leave. Thank you for joining.